Planck time, the smallest observable unit in which we can describe the universe. The cataclysm we call the Big Bang generates space and time, matter and energy. At this moment, gravity separates as the first of the four forces that define our laws of physics. It's a puny force compared to its future compatriots, but the reach of its power is infinite. For an incomprehensibly small fraction of a second, the universe is a nearly infinitely dense, nearly infinitely hot fireball. Then, the strong force breaks off to become the second of the four forces. Its power is tremendous, but its reach is incredibly small, only as far as the sizes of the subnuclear particles it binds. We learned of its strength when we first split the atom. The remaining two forces have still not yet come into their own. Then, all of a sudden, the universe increases in size by a factor of at least 10 trillion. It inflates. Things that were once close together are now spread so far apart that it might not even be possible that it could ever communicate again before the end of the universe. Even light traveling at its maximum speed may never get from one end to the other in that time. It's now that big. And it all happened within 1/1,000,000th of 1/1,000,000,000th of 1/1,000,000,000th of a second. How do we know inflation happened? The universe has a flat geometry today, and a super fast expansion like this one is one of the few ways that could have made it so. But no one really knows why that is yet. Inflation is still a model in search of a theory. Imagine an explosion and think of the light from that explosion as the inflation of our universe. Now, think of the sound from that explosion as the light in the universe. Even after the inflation stops, the light may never catch up. So, space itself expanded everywhere, and in every single spot there was that same infusion of energy. Now, you might think that the Big Bang occurred and that for 13 billion years things have been expanding out, and that these 13 billion years are all that is. It's as if I turn on a light and let that light travel for 13 billion years in all directions, and that marks the whole size of the universe. Well, that's only a very, very small part of the universe. No, the cosmos is way bigger than that. It's much richer than that. Let's put it this way. If you and I were right next to one another, and then inflation occurred, we might be carried so far apart that 13 billion years later, I would have a big bubble of space around me that I'd be aware of, and you would have a big bubble of space around you that you'd be aware of, but we would be so far apart that time would have to go on for a long while before it would even be possible that we could communicate. It's as if this room were the size of the universe, and we could only see this much of it. A small bubble of space, 13 billion light years in radius. That's tiny compared to this room. That's it. That's the smallness of this tiny piece of the universe that we can see. What's out there beyond our reach is so big that it's almost indescribable, almost incomprehensible, almost 10 trillion. That's a big number.